Okay, so we've learned earlier on in the course that the hardest particle to discover was the nucleus, the neutron, purely because it had no mass, no charge. Okay, now we realize that, and it was found that it has a mass of 1 atomic mass unit. So the thing then about isotopes and what we're looking at here is, I'm on page 83 of the Formula and Tables book. So you'll notice that every element is listed, but every element is listed a couple of times. So one that we've spoke about a couple of times already is this. Okay, so this is carbon. So you can see here that carbon has 3 isotopes, 12, 13 and 14. Now the two that we're very familiar with is carbon 12, is the most abundant one. So the abundancy is here. So 98.93% of the carbon that we find around us is this one here, the 12, carbon 12. Then we also see we have this carbon 14. Okay, and carbon 14 has a mass there, as you can see, a little over 14. And we'll see a figure after it here. It has a half-life, which means it's radioactive. Okay, so basically it gives off radiation, and its half-life is 5730 years. So it takes 5,730 years for half of it to decay. So if you started off with 10 grams, in 5,730 years, you would only have 5 grams. The rest would have been emitted as radiation. So every element, generally you can see here, has different isotopes. There's neon. Aston did work with neon, so we have 3 isotopes there. Moving on to the next page, we have sulfur there. It has 4 isotopes. Argon there has 3 isotopes, and so forth and etc. Okay, so now this should help you then to discover, so they all have whole numbers here for their atomic mass number, because that whole number is telling you the number of protons and neutrons. So if we go back here to something like, we'll go back to our carbon example again. So carbon here has, every carbon has 6 protons. Okay, so because this one has a mass of 12, it also has 6 neutrons, whereas this one will have 7 neutrons and this one will have 8 neutrons. So the 13 and 14 will be heavier than the 12. They will still contain the same amount of protons, but 6 neutrons for the first one. So 6 neutrons. This one here will have 7 neutrons. And finally, this one here will have 8 neutrons, making it heavier. Okay, so what we're going to do then is we're going to now figure out where the decimal answers came from in the tables book that we use today. And it's from a very, very simple calculation of getting the averages. Now, it's not enough just to add up the 3 figures and divide by 3, because they're not in the same abundance. Okay, so when things are not in the same abundance, we can't just add and divide. Okay, so I'll use a simple example here. So this is one that I've taken from that page for magnesium. So what we do is we say that we have, so 78.99, that's there the percentage abundance. So we'll say that we have 78.99 atoms will give us a mass of, so we go on and do 70, or we'll take our 24 and we'll multiply that by 78.99 and we'll get 1895.76. So now I'm using these figures up here. Okay, so these are the figures that I'm using here. Okay, and then for my percentages, it's here. Okay, so the next one then is 10 atoms. Now I'm just calling these atoms, you could call a percentage either, of 25 mass, and I have 10% of those, so I'm multiplying those by 10, so that's 250 they would have a total mass of. And then my last one, 11.01 atoms, will be equal to, so I'll just highlight those again, will be equal to 26 this time, and it's by 11.01%, So that gives me 286.26. Now, adding these up, this will total 100 atoms. And this will total 2432.02. So this implies that one atom would obviously have a mass of 2432.02 divided by 100, which is 24.3202. Now, you'll note it's not exactly what's quoted in the tables book, okay, because there's probably better rounding done. Rather than 2 decimal places here, okay, for these abundance, they probably did calculations with more decimal places, giving them better accuracy down here. Now remember, atomic mass units do not have any, relative atomic mass does not have any units. So the AR of that is equal to 24.3202. So one more then simple example. So this is taken from the exam papers. Okay, so it's calculate to 2 decimal places the relative atomic mass of a sample of neon shown by a mass spectrometer composed of 90.50 and neon 20 and 9.5% of neon 22. Okay, so we'll do it in the exact same way as the last one. Okay, so all we're going to do is see what the mass of 100 atoms are. Okay, so I'll take my 90.50 atoms would equal to take their mass and multiply them by 90.50. So 90.50 multiplied by 20 is giving me 1810. So then I have 9.50 atoms. And that will equal 22 multiplied by 9.50. So 22 multiplied by 9.50 is 209. So if I total the two of those, I'll get 100 atoms. And this will give me 1810 plus 209, which is 2019. Will give me that. So that implies that one atom will have a relative atomic mass of 20.19 atomic mass units. Okay, or sorry, just no units at all. So 20.91, because you're just relating it back to the mass of carbon.